Okay, part one on conservation of energy problems. We've got a 20 kilogram block, and it's at rest, and it's pulled across a rough surface with this friction by this force and this angle for 20 meters. What is the work done by each force? What's the work done by friction? So the friction acts 180 degrees from the displacement, so the friction is going to be negative. You could put that in the equation, but as soon as I see that's 180, I know that friction is going to be negative. So the work done by friction is the force of friction times the distance, and friction is mu times normal times d. But the normal, well, we've got to find the normal. It's not mg. And that's because of this applied force. So we do sum of the forces in the y direction equals 0. The up force is the normal. The other up force is F sine of theta. And that equals the one down force, which is the weight. So the normal force equals the weight minus F sine theta. So, yep. So the normal equals the weight, which is 200 newtons, minus F sine theta. So I ran out of room here. We'll say 100 newtons times the sine of 36.87. Am I going to run? Here we go. Yep, we're going to run out of room. 200. Let's just start all over. So the normal equals 20 times 10 is 200 newtons minus F 100 newtons sine of 36.87 degrees. That normal is 140 newtons. So the work is mu that is given as 0.10 times the normal 140 newtons times the distance, which is 20 meters, and you get a work of negative 280. Now remember, I'm making it negative because the work done by friction is going to be negative because the angle between the friction force and the movement, the displacement, is 180. So I slapped the negative on it. Friction does negative work. Negative work. What's the work done by the 100 Newton force? Well, the 100 Newton force acts at an angle, so it's 100 newtons. Well, so it's the F applied times cosine of the angle given. That force acting in the direction of motion times 20 meters. 100 newtons is the applied force. Cosine 36.87, that's the force acting in the direction of the motion times 20 meters, and you get 1,600 joules. That's the positive, of course, because that horizontal component acts in the same direction as the displacement. So that's 60. So you've got the positive work. What's the combination of the two? You add them up, and you get 1320 joules. 1320 joules. All right, what is the speed of the block as a result of these two combined forces after 20 meters? Well, the net work did what? It didn't make the box go higher or lower. It only changed the kinetic energy. So whatever work you did, which is 1320 joules, did what? It changed the kinetic energy. 1/2 mv squared, now it's vf squared, minus vi squared. Now we're told the vf is, the vi was 0, so that's 0. So that positive work, the net work was positive. 1320 equals 1/2 m times what's the v squared? That's what we don't know. What was the mass of the box? It was 20 kilograms. Really should be two significant digits. 1320 joules equals, well, let's make it 1/2 20.20 kilograms, even though the picture only shows 1. Vf squared. If you ever had a problem for me, I'd get all the significant digits correctly, and the Vf equals 11 meters per second. Oops, not second squared, but 11 meters per second. Let's test this. So you've got I multiply both sides by 2 to clear the fractions. So 1320 times 2, and then divide by 20, and then take the square root of that. Yeah, I get 11.4. This next one's a real challenging one. We have a 20 kilogram block, slides across a horizontal frictionless floor, then slides up 10 meters along the rough. So this is a rough incline until it comes to a stop at the peak. What is the initial speed of the block prior to sliding up? Okay, so what do we have here? It's frictionless here. So the only energy we have here is kinetic. And what we have as it's going up is we've got the object gaining potential energy, and then it loses kinetic. So the work is done on my system. So I write the equation. When work is done on my system, the energy does not stay the same. In fact, the work done on my system is always equal to all the energy changes. This work, of course, is friction, and it's equal to the kinetic energy change plus the potential energy change. Why do I say potential? Because it's changing height. Why do I say it's kinetic energy change? Because naturally it's going to change. It's going to lose kinetic and gain potential. So that is the work energy equation. So let's see. What is the work done against friction? It is the force. This gets so complicated. I think we're going to separate out all of this one by one. What's the work done against friction? Let's do that separately. The work done against friction is the force of friction times the distance, and you're told this is the distance the work is done. So the force of friction is mg cosine theta. That's mu. There's the friction. Right there is the friction multiplied by d. All right, like I said, I think I'm going to separate. There's so much going on here. I like to take it in pieces. Let's find the work done against friction. So it's mg, so it's 20. That times 10 is 200 newtons, times the cosine of 36.87 degrees, times the distance that was given, which is 10 meters. That's how much work is done against friction. Okay, so that is, what I realized I left out? Left out my mu. Let's put that mu in there. Mu is 0.20. Let's stick it at the end where it doesn't really belong, but I left it out. You see the mu is over here. So let's do the calculations. So the work done by friction is a negative. Of course, friction's negative because it's working in the opposite direction of the displacement. Now let's also get the change in potential energy, which is not super easy. It's mg delta h, but you don't know what this h is. But you can use trigonometry to get the h, can't you? Because you got a right triangle, so we've got to find the h. Um, h is actually 10 meters times sine of the 10 meters are here, times the sine of this angle, 36.87. So let's do that work, find the h. This height is 6 meters. So now we could find the increase in potential energy. So that is, let's do that separate. We'll put in the equation. So the increase in potential energy. When you have a lot going on, it's probably best to just pull everything out. So the m is, 20 kilograms times g, which is 10 meters per second squared, times the h, which we found out to be 6, we'll call it 6.0 meters, and that is 200. So that is 200 times 6 is 1200. Let's see. Yeah, that's 1200. 200, 1200. So you get a gain of 1200. Now, what's the change in kinetic energy? Okay, well, actually, what we want to find is the initial speed. So if I'm going to find the initial speed, I need to know the change in kinetic energy. I know that the So if we're going to find the velocity down here, we need to know the change in kinetic energy. We do know the work against friction, which is negative 320. Rather than put it over here, I'll just put it over here. Negative 320 joules. That's the work done against friction. That's that negative work. So what we do is define the change in KE and then ultimately try and find the V. We subtract 1200 from both sides. And we get negative, let's see, 320 negative minus 1200. So the change in kinetic energy turns out to be negative 1520. That's negative 1520 joules. And we are clearly out of space. So now we have to turn that into delta KE equals the 1/2 m v f squared minus vi squared. So that's negative 520 equals 1/2 of the m is given as, let's see, 20 kg. Now the VF is 0 because it stops at the top, times minus, whoops, so it's 0 minus the VI squared, which we don't know. Whoops, that's VI squared. So what I'll do is I'll divide, this is just 10. I'll divide by 10, and then I'll take the square root of 152. And you get 12.3. VI is 12.3. We'll call it 12 meters per second. Whoa. We have to go over this again, and we'll stop right here. So the concept here is when work is done on by a system, the energy of the system changes. What kind of energy change do we have as it slid up the hill from the bottom to sliding up the hill? Will it change PE and KE? When you have a problem like this with a lot going on, separate out everything. Like separate out the work done against friction, which is work done by friction. Mg cosine theta is normal times the mu times the d to make it a work, and you get negative 320. Okay, that's your WF, and I put that over here because I ran out of room over there. Now, what's the change in PE? They didn't give you the H, so you got to use 10 meters times sine of theta because the H is the opposite the angle. So then it's just, here's your MGH. M given is 220, G is 10, H we found is 6. 1200 is the change in PE. That's a positive change. So I put this over here as a positive change. So I have an equation here, and I solve for the change in KE, and I got this. And I use 1/2 mv squared, that's down here, and it is 12 meters per second. So that's quite a problem. We'll stop right there because your probably head is hurting now, because mine is.